Okay, freshmen, we are going to start now a properties of water lab demonstration. So some of these different stations are going to showcase water's unique properties. First of all, these unique properties are essential to life on Earth. You'll see that in the notes. And secondly, these unique properties are going to be the basis for your planning lab. And so it's important that you recognize, first of all, what these unique properties are and how they can be displayed, and then also ways that we can maybe manipulate these properties and turn them into measurable variables, and then that would lead easily into your lab report. Okay, so you have a worksheet that you should be following along as I go through this demonstration. We're going to start with station 1, which is all about cohesion. Cohesion is caused by the intermolecular attraction between like molecules, that means molecules that are the same, like two water molecules, within a body or substance that unites them. Water has a high attraction to other water, so that means that water has high cohesive properties. This allows water to be pulled along a pathway with relative ease. An example would be our blood being pumped through our body and the cohesiveness of the cytoplasm in our cells, and our cells being mostly water. So basically cohesion is the idea that water wants to stick to other water, and I'm going to showcase this by taking water and putting drops on a nickel. I'm going to attempt to squeeze out 30 drops on a nickel. One, oh, you can't see that one. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 30. There we go. 30 drops of water on a nickel. We can try to see this on a closer scale. You should be able to see, oh, sorry. That the water has made a dome on the nickel. The water is holding onto other waters. It's actually resisting the force of gravity by holding on to other waters instead of falling off the nickel. Now, to compare that, I'm going to show you with alcohol. Alcohol is a nonpolar molecule, so it does not have the same cohesive properties as water. So I'm going to take another nickel. There's our water molecule. If I can move this. Nope, I broke the cohesion by touching it. Let's see how many molecules of alcohol we can fit on the nickel. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. Oh, I almost got to 30, but we did see that the cohesion was not as strong as water. Water, I got to 30, and it showed that strength of cohesion, where alcohol, I actually got more drops on that than I was expecting. It's also possible that one drop of alcohol is going to be slightly smaller than one drop of water because, again, those cohesive properties, I'm not sure if you can tell the difference. Drops of water and drops of alcohol. I think the alcohol drops do look a little smaller. But anyways, alcohol was not able to hold on to other alcohol molecules the same way that water was. Okay, so go ahead and pause the video and answer the 3 questions on the lab document. Okay, the next station, station 2, is on adhesion. Adhesion is the process between dissimilar molecular species that potentially bring them in direct contact. By contrast, cohesion takes place between similar molecules. So the cohesion of water would be water holding on to other water molecules, whereas the adhesion of water is going to be water's tendency to hold on to other molecules, non-water molecules. Water is very adhesive. We know that gravity pulls everything on Earth downward, but adhesive properties of water are strong enough to defy gravity, such as moving upward through a plant. So the capillary action of water moving from the roots of a plant, of a tree, from the roots all the way up to the leaves, that would be an example of adhesion. So to show adhesive properties of water, I'm going to show two different materials, wax paper and paper towel, and I'm going to hold them in water for 45 seconds each. Okay, so I got my water, I've got my paper towel, I've got my wax paper. I tell you what, why don't we let this go for like a full 2 minutes? You don't have to sit here and wait for 2 minutes, so I'll pause the video and restart in 2 minutes. Okay, so it's been a few minutes and we noticed that the paper towel is completely wet. So this right here is soaked through, even though it never made contact with the water. The paper towel was only like up to here, meaning the water went against the force of gravity up the paper towel because of those strong adhesive forces. Now, differently is the wax paper. The wax paper has a hydrophobic barrier, hydro meaning water, phobic meaning scared of. So a non-polar barrier that does not have adhesive properties with water. And so the wax paper is completely dry. And even down here, the wax paper, it has water on it, but you see the water is basically like wicking off. It really didn't absorb water at all. Okay, so you can now answer the 3 questions that go along with station 2. Okay, station 3 is on density of ice. Another amazing property of water is that it expands as it freezes and contracts as it melts. Almost everything else in nature contracts when it freezes and expands when it melts. Water is the opposite. Since in the notes, by the way, you'll learn how that happens and why. Since the same amount of water takes up more space in the form of ice, ice has less density of water. So when I put ice into water, what do you think is going to happen, knowing that that liquid water expands when it turns into solid? So because it expands, it means the same amount of weight is taking up more volume, meaning that ice floats on top of water. In comparison, alcohol, ice, and we see that the density of ice, even expanded water, is still more dense than alcohol, hence why it sinks. Okay, looks like you have 2 questions for this station. Again, ice in alcohol, ice in water. Okay, station 4 on surface tension. It's important to note that surface tension is a subcategory of cohesion. Surface tension is basically due to cohesion, because of water's cohesion, water's ability to hold on to other waters, that results in high surface tension. So surface tension is the property of a surface of a liquid that allows it to resist an external force. Some objects can float on the surface of water even though they're denser than water. And in the ability of some insects, such as water striders, they can even run or stand on top of water. This property is due to cohesion of like molecules, and it's responsible for many of the behaviors of water. Okay, so what we're going to do here is we're going to try to test the cohesion of water by taking a paper clip which is definitely denser than water. Like if I take a paper clip and just put it in water, it sinks down to the bottom right away. But if I can gently lower this paper clip on the water, we should be able to see the high surface tension of water. This takes a steady hand, so it might take me a few times. You guys can practice this at home. It's kind of cool if we can get it to work. All right, so we see that the paperclip, again, which is metal, it is definitely denser than water. It is actually spreading out and not able to break the surface tension of water. I want to kind of zoom in so you guys can see that it's sort of bending the surface of water. You can see that the paperclip is pushing down on the water due to gravity, but not strong enough to break the cohesion. You can sort of see the bending of the surface of the water, but it's not breaking. Okay, if we're to try this with alcohol, lack of cohesive forces, lack of surface tension. I could have the most steady hand in the world. I could try this 100 times and it's never going to sit on the surface. It's always going to sink to the bottom. All right, station 4, you have 3 questions to answer. All right, station 5, dissolving a solute. A solution is a type of mixture where one material dissolves another. The material that dissolves is called the solute. The material that does the dissolving, or the material that makes the other thing dissolve, is called the solvent. Now, water dissolves a lot of things, and because of that, we call water the universal solvent. It can't dissolve everything, but if you think about our body, the way that we're able to ingest, consume our food, and then break it down, a lot of that is due to water's ability to act as a solvent and dissolve those different things. So for this demo, again, we're going to have water compared to alcohol. And we're going to put about a tablespoon of salt into both of these. So tablespoon of salt into the water. And we see that the majority was able to dissolve. Let me turn the camera up. You can still see there's a little bit of salt at the bottom that didn't dissolve. That might be because water reached its saturation point. It's possible that it was too much salt to be able to dissolve, but actually it's like when I gave it another stir, the salt is pretty much all dissolved. Okay, comparing to alcohol, our non-polar liquid, pour the salt in, stir it up. Now I can even feel the difference. When I was stirring the water, I didn't really feel the salt. Like after those first couple stirs, I didn't feel it, but I can still feel the grittiness of the salt. It still feels like I'm stirring like sand. If you imagine putting sand in water, you can stir forever and the sand's not gonna dissolve. It's gonna be a mixture, not a solution. So anyways, we see the fogginess, maybe a little bit of dissolving right there, but if you can look at the bottom, it'd be hard to see. You can see all that salt just sitting there in the bottom. Actually, you know what? Let me stir one more time. And it might take a minute to settle, but I'll wait. Here's the water again. Let's wait for it to settle. So I'll pause it for 5 minutes and then we'll check back. Okay, so I let plenty of time elapse just to show, and we'll try to look from like a vertical. See it? Yeah. In the water, which is the blue one, we really don't see anything left. There's like a little bit of salt in the very middle that maybe didn't dissolve, showing that water's dissolvability. The alcohol, I think pretty much all that salt is still there, sitting at the bottom, not able to dissolve. Okay, 2 questions for dissolving a solute. And now on to our last station. Okay, station number 6 is called high specific heat. I have Professor Lambden here helping. This one is dealing with heating and cooling liquids. I'm not allowed to use the hot plates by myself because of the incident, which I'm sure you guys are aware of. Okay, anyways, water has a high specific heat. What this means is that water can absorb a lot of heat before it gets hot. This is why water is valuable to industries. This is why water helps moderate Earth's temperatures. The high specific heat index of water in oceans is going to help gradually warm the Earth during wintertime and cool the Earth during summertime. In this experiment, we're going to compare the specific heat of water versus the specific heat of alcohol. So we are currently using probes to record initial temperatures before they go on the hot plate. And the initial temperature, which one is water?
We'll find out in a minute.
Okay. The initial temperature for water is 20.8, and the initial temperature for alcohol is 20.8. So we are starting with an initial temperature of 20.8 degrees Celsius. We're going to put these both on the hot plate. I wanted to pick the smallest hot plate that we have.
Yeah, thanks. Appreciate that. There we go.
All right, and so what we're doing now is we are heating up both the water and the alcohol. And if we look at Mr. Lambden's screen, we can see the alcohol, which is temperature 1, is rising faster. It's already at 30 degrees Celsius. Water, which is temperature 2, is rising, but much more slowly. It's at 29 degrees. I'm going to switch with you. There we see the temperature of alcohol continuing to rise. It just hit 40 degrees. Because alcohol does not have high specific heat, it can much more easily be heated. Water with high specific heat is heating at much slower. So I'll tell you what, why don't we wait till alcohol gets to 50 degrees and we will call that our final temperatures. All right, so final temperature for alcohol, 50 degrees. Final temperature for water, I think it was at 37.9. Water clearly takes more energy to heat and cool, whereas alcohol, without those unique properties, can be heated or cooled much more quickly. Okay, good job to Professor Lambden, he's allowed to use the hot plates. All right, and you have 3 questions for Station 6. That's it for the video. Good job, guys. Hope you enjoyed that demo.